Hi everybody, today we are going to do a very basic overview of sequences and series. So a sequence is simply a list of numbers that can be given by a specific rule or equation, which is usually written in terms of a sub n. So for example, this would be an example of a sequence. So it's important to understand the difference between a sub n and n. So n is the relative order of the terms. So if you have n equals 1, it would be your first term. If you have n equals 5, it represents your fifth term. So it's kind of the place in line. And then whatever a sub n is, it is the term, the actual term of the sequence. So it's just really important to know that n represents the place in line and a sub n is what the actual term is. So if we want to find the first four terms of this sequence, all we have to do is first substitute a sub 1, and then we'll substitute for n equals 2, so on and so forth. So if we substitute for n equals 1, we end up with negative 1 on top, and then 2 plus 1, which is 3 on the bottom. For a sub 2, if we have negative 1 squared, it becomes positive 1, and 4 plus 1 is 5. For a sub 1, it becomes negative again, and then 7, and then a sub 4 is 1 over 9. So it's just plugging in those n values to find the first four terms, and then we simply list them with commas in between. That's how you write the terms in a sequence. So those are the first four terms of this sequence. Now, you can also write sequences a different way. So just to remember that previous type, they were written in terms of their place in line. Are they the first term, the second term, third term? They were written in terms of n. Now, a different way to write them is called a recursive sequence. And recursive sequences, the terms are written in terms of previous terms. So there's two dead giveaways that something is written recursively. One, since you're writing it in reference to a previous term, you do have to define the first term. So if you see something like this, it's a good idea that it's probably recursive. And then the second dead giveaway is a term like this. So like a sub k minus 1. Really, this just means the term before. It's one space before the space you're trying to find. So this is an example of a recursive sequence. It's written in terms of a previous term. So let's try to find the first five terms of this. Well, a sub 1, our first term is given to us. It's 3. To find a sub 2, we do 2 times, well, a sub k minus 1 would be a sub 1, the previous term. So we're essentially taking this and using it to find our next term. And then plus 1, so we get 7. And then to find a sub 3, it's 2 times a sub 2, which is 7. So our previous term, plus 1. So we have 15. So you can probably see that this pattern will just continue. So we'll have a sub 4 is going to be 2 times 15 plus 1, so it's going to be 31. And then a sub 5 is going to be 2 times 31, the previous term, plus 1, so 63. And then, of course, we can list out our terms as a sequence. So 3, 7, 15, 31, 63. So those are the first 5 terms of this recursive sequence. So it's just a different way to write your terms. I did just want to talk about a really famous recursive sequence, which you've probably heard of before. It's called the Fibonacci sequence. So here's the formula for it. And notice it says a sub k minus 2 plus a sub k minus 1. So the Fibonacci sequence is essentially the sum of the 2 previous terms. So here we're not only writing it in reference to the term before, but also 2 terms before. And since we're writing it in reference to 2 terms before, you do need to be given the first two terms. Now here you see a sub 0. Some sequences you will start at n equals 0 or k equals 0, whichever variable you're using. Most you start at 1, but some start at 0, and that's just the different way to represent the first term. So we can start listing out some terms of the Fibonacci sequence. The first two terms are given. So the third term is the sum of terms 1 and 2. So which is 1 plus 1, which is 2. Then our next term will be the sum of the 2 before it, so it's 3. Then we do 2 plus 3 is 5, and 3 plus 5 is 8. So it follows that. So I just wanted to show you just this really well-known recursive sequence, which you probably have seen before, and you probably even described, not even realizing that you're describing a recursive sequence. Another thing we're going to be working with in sequences and series, and also when we start doing permutations and combinations, are factorials. So this says if n is a positive integer, that's very important, then n factorial, by definition, is 1 times 2 times 3 times, all the numbers in between, times n minus 1, the number before n, times n. So you essentially multiply all of the positive integers up until n. So I know that this definition is written from 1 going up, but I think typically it's a little bit easier to think of it from n going down. So for example, 5 factorial is just 5 times 4 times 3 times 2 times 1. That's by definition what a factorial is. Now, one special case that you will come across is 0 factorial. So 0 factorial is defined as 1. So let's try writing the first 5 terms of this sequence, which does have a factorial, and we're going to start with the term with n equals 0. So let's find a sub 0. So we have 2 to the power of 0 over 0 factorial. So 2 to the power of 0, remember, is 1. 0 factorial is 1, so it's 1. So those are two special cases that you have to know how to manage. So a sub 1 will be 2 to the power of 1 over 1 factorial, which is 2 over 1, so 2. A sub 2 is going to be 2 squared over 2 factorial. So 2 squared is 4. 2 factorial means 2 times 1, so 2. So we have the same term for the second and third, but that's totally fine. For a sub 3, we'll have 2 cubed over 3 factorial. So we have 8 over, so remember 3 factorial is 3 times 2 times 1, which is 6. And here we do have to simplify to 4/3. And then let's find our fifth term, a sub 4. So 2 to the power of 4 over 4 factorial. 2 to the power of 4 is 16. 4 factorial is 4 times 3 times 2 times 1, so 24. And that will simplify to 2/3. So you can list those terms out as a sequence. Now we're going to talk about how to simplify expressions that have factorials. So when you see something like this, you actually don't need to go and multiply out all of 8 factorial and then all of 2 factorial and then all of 6 factorial, because since we're just multiplying everything, we really just end up with a bunch of factors. And here you will see that we will end up with factors that in fact cancel each other out. So first I'm going to focus on these two terms together. So if you start listing out 8 factorial, you have 8 times 7 times, and you have 6 times 5 times 4 times 3 times 2 times 1. So that 6 going on down, we can just write as 6 factorial. And the reason why we might want to do that is because in our denominator, we have 2 factorial, which is 2 times 1, and then we actually have times 6 factorial. So these actually cancel each other out. So the 6 factorial in the denominator cancels out everything 6 down from your numerator. And then here we can simplify as well. And all we have left is 4 times 7, which is 28. So you can see there's definitely a more efficient way to simplify terms with factorials than just multiplying everything out and simplifying from there. Now let's look at this next one. We have n factorial over n minus 1 factorial. So I think a nice way to approach this is let's think about what would happen if we used real numbers for n. Like let's say if we set n equal to 10. If n were equal to 10, our numerator would say 10 factorial, our denominator would say 9 factorial. And you can see that this number in your denominator would cancel out everything 9 down, so all we would have left is 10. Well, let's see, what if n was 22? In our numerator, we'd have 22 factorial. In our denominator, we have 21 factorial. 21 factorial in the denominator cancels out everything 21 down, and all we have left is 22. So you might see that when it simplifies, it's always going to be that n value that we chose. So you can probably guess that this will also simplify to n. But just a different way of looking at this, if we expand it out a little bit, n factorial by definition is n times, and then you go down to the next integer, so n minus 1 times n minus 2 times n minus 3, and then so on. And then in our denominator, we have n minus 1 times the next number integer down, so n minus 2 times n minus 3, so on and so forth. So you can see which parts cancel out, and once again, all we have left is n. So whether you want to actually expand it out, or whether you kind of want to reason your way there using maybe real numbers to test different values, you should end up with n. All right, go ahead and give this problem a try. Pause the video. Okay, here you should end up with 4 times n plus 1, or you can distribute it and say 4n plus 1, or 4n plus 4. So here you can see that this 3 factorial on the bottom cancels out everything 3 and down, so leaving us with 4 in the numerator. Now here, this is n plus 1, and this is n. So if you expand out n plus 1 factorial, it's n plus 1 times 1 below that, which is just n times n minus 1 times n minus 2, so on and so forth. N factorial is n times n minus 1 times n minus 2. You can see what cancels out is everything n down, but n plus 1 is still left. So all we have left is 4 times n plus 1. All right, so another thing that we're going to start working with is summation notation, or sometimes called sigma notation. This is a sigma. So this is just a way to represent what's called a series. So when we're going to be actually taking the sum of the terms of a sequence. So this notation tells you a few things. This bottom number tells you the lower limit of your summation. It tells you which term to start with. So typically you'll see that it starts, you have something like I equals 1 telling you to start with the first term in your sequence, but not always. But this will tell you which term they would like you to start with. And this number on top will tell you which term they would like you to end with. So this, you're ending with the nth term, whichever number that is. And then this right here tells you what your sequence actually is. So it kind of tells you where you're going to get your terms from. And then you just add them all up, and then your sum is your answer. So this is summation notation or sigma notation. It is possible to have an infinite sum. It doesn't work for every series, but it does work for a few. So let's give these two a try together. So here you can see that we have our summation notation for this sequence right here. So they're essentially asking us to find the first, second, third, fourth, and fifth term, so first through fifth, and add up all those terms. So our first term is 3, and then 6, and then 9, and then 12, and then 15. So those are our first 5 terms. This is when I is 1, I is 2, I is 3, so on and so forth. And we just add those up and we get 45. And that sum is our answer. Now you might notice in this problem, they're asking us to find 3rd through 6th terms. They want us to find the 3rd, 4th, 5th, and 6th terms and add those up. So like I said, you don't always start at the first term. So our 3rd term is just 1 plus 3 squared. So we have 10, our 4th term is 17, our 5th term is 26, and our 6th term, is 37, and if you add those all up, you get 90. So that's the sum of terms 3 through 6. All right, go ahead and pause the video and see if you can find this sum. Okay, so here you can see that they found the first, second, third, and fourth sums, and just add it up, and you should end up with 44. So here are some useful properties of sums that we'll be probably using later on in this unit. So the first one, if you're taking the summation of a constant. So if your sequence is a constant, essentially what you're saying is that every single term is that constant. So it's just C, 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 C. Every term is that constant. So if you have the sum of a constant, you're just essentially multiplying your constant by however many terms you have. Because if your constant is 2 and you're doing 5 terms, you just do 2 times 5. Here, notice that we have a constant multiplied by your sequence. So you can actually multiply it and then find that sum, or you can find the sum of your series and then multiply it by the constant. So this could be something that will save us time, because as you'll see later on this chapter, there are actually formulas that we can use to find sums. So rather than doing it by hand, we can quickly do a formula and then multiply it by the constant. You can always pull that constant out front. If you're doing summation notation with the sum of 2 separate sequences, you can actually find them together or split them up separately and then add up the 2 separate sums. And it works the same if you have a difference. So these can just be some little tricks to save you some time. Now, all of these summations that we've been doing are technically what are called series. So a series is essentially when you take the sum of the numbers in a sequence. So a series is written using summation notation. And essentially the only difference between a series and a sequence is a sequence has commas between your terms and a series has plus signs between your terms, showing that you're adding them up. Now there are different types of series. There's what's called a finite series. So a series between a specific starting point and a specific ending point. So then you would just find all those terms and add them up. So that's called a finite series, or sometimes it's called an nth partial sum of a series. Or you can have an infinite series, and you're essentially adding all of the terms all through the infinite term. And there are very specific groups of series that you can actually find the sum even when they are infinite. So that's something that we'll talk about in the future. There's a formula for it, which is nice. So let's look at this summation problem. So here we have an infinite series, and here's what our sequence is. And the first thing they ask is to find the third partial sum. So they're asking us essentially to find a finite series from term 1 to term 3. So we can find this by listing out our terms. So 3 over 10 to the first power is just 3/10. So we could say 0.3. 3 over 10 squared is 300. So we could say 0.03. And then we have 3,000. So 0.003. So if you add those up, it's just 0.333, which might look a little bit familiar to you. Now, the second part B, they actually just want you to find the sum. So they actually want you to find that infinite sum. So imagine we kind of continued this pattern of 0.3 plus 0.03, and then we just keep adding zeros, right? And then we just continue that on. You might guess that what we end up with is just 3, 3, 3, 3 repeated. And this is actually a decimal that we know very well. It is 1/3. So that sum of this infinite series is 1/3. And this is something that we did cover last year. It is possible to take any repeating decimal and write it as a fraction. So that might be something that you would want to go back and review from last year and find that old video, because it is something that will be useful to know. And it's not necessarily something we will talk about during any of the slides, but it might show up in a homework question. So I would go back and try to review how to turn a repeating decimal into a fraction. All right, go ahead and pause the video and give this last problem a try. Okay, so if you find that partial sum from term 1 to term 4, you should get 0.5555. So you can guess as that becomes an infinite sum, it's going to be 5 repeated, which you may or may not know to be the fraction 5/9. So once again, I would definitely go back and try to review how to turn a repeating decimal into a fraction. All right, that is all for today. Thank you so much for watching.